Okay, can everybody hear me? Okay, I guess yes. Great. Okay, so let me first thank the organizers for making this event possible. So today, well, let's see. So I'm going to give you a little bit of entertainment. So it's after the lunch, so it's nice to relax. And I'm going to talk about Parton showers. And let's see, so where the okay, this is the so this work is in collaboration with Christian Bauer and Soichi Gusa at UC Berkeley. And and what I'm going to talk about is, well, first inspired by this paper by Christian et al. In 2019 about applying quantum algorithm to Parton showers. And then, so at this point, there was no application, no actual application to physical problems. And afterwards, all the papers Sochigusa pointing out that in some models beyond the standard model, these algorithms can be very useful, and it might have dramatic consequences for search for some dark sector models, which I think is interesting. So that motivated us to look into more deeply into the quantum algorithm behind it. So there was an algorithm, but that wasn't the most detailed one. And we tried to make the model realistic, and that's how we came to this collaboration. Now, so this is well, okay. So to this audience, I don't think I need to motivate why quantum simulation is interesting, etc. So let me come to the topic itself. So I'm going to discuss the quantum Veto Parton shower. So what are these? Well, you can just decompose. Well, first of all, there is a word quantum. So it's a quantum algorithm, using quantum computers, etc. In practice, it's actually quantum classical hybrid. That's the philosophy. If there is something you can do with easily with a classical computer, you should just do it. Now, there is also a word veto, which is actually the most novel part of a paper. And so it's about the veto algorithm Monte Carlo, which we incorporate from the literature on the classical Monte Carlo. And then there's a Parton shower, which I'm going to explain the idea. So don't worry if you don't know about it. But at least it's some problem which comes from high energy physics. It happens all the time in colliders, and people use some software to simulate this all the time, actually. So, well, let's see. So this itself is interesting in my opinion, but let's see. Perhaps many of you are not interested in Parton shower per se. Well, in that case, I would say that the point here of my talk is that some of the things I'm going to say, and hopefully I'm going to explain in the end the toy model, etc. The point of what I'm going to say is hopefully something of a more general interest. So what I'm going to talk about, you can formulate as a general question of what you're going to do, whether to introduce the veto algorithm to, so sampling from some probability distribution specified partly by quantum states. And formulate that way, I wonder if this type of technique can be applied to broad problems. And in fact, I try to find if somebody has done that before in the literature. Maybe somebody has done that. Please tell me if somebody has done that. But otherwise, it's interesting, cool to find any problem where this type of technique can be applicable. So I'm happy to discuss on that. But let's see. So today I'm going to talk about the specific problem of Parton shower. And let me start with the classical Parton shower, which is what people do all the time. Now, the problem is simple. So here there is something which is called a dark fermion. And anyway, it doesn't matter. There is some fermion, some particle coming in. And then sometimes it emits a photon. And it happens probabilistically. Sometimes it happens, sometimes it doesn't happen. In this case, there are 3 photons emitted, and there is a probabilistic process. And well, so okay, so we want to simulate this, right? So, and then how we do that? Well, you can try to divide everything into steps. So here you can think of this axis as a time, and or if you like energy. So you start with some very high energy state. Where a particle comes in, you gradually lose energy, and all the way to somewhere here. And there are not too many orders of magnitude difference. It's just a couple of orders of magnitude. And so you're not going to consider the full everything. So we are looking at the part of the problem. And there is some theorems which guarantees the factorization theorem, etc., where what happens beforehand and afterwards, you can kind of decouple. So you can concentrate on this particular part of the problem. Now, things are divided to different time steps, and each time step, there might be emissions. In this case, there are 2 emissions, for example. But that's because the time step is a little bit too crude. So you can try to make it a little bit more refined. And if the time step is sufficiently small, you expect that it's very likely that only one emission, at most one emission, happens during each time step. Well, there are multiple time steps, but that's going to be smaller, so you can neglect it in some approximation. And the question is how you're going to discuss that. Now, at this point, it seems easy because it's just probability, so it's like very easy. But the actual situation is a little bit more complicated and requires a sampling, etc. And one of the reasons is that there is a little bit more data. So what is the data? Data of the energy of the particle. So when the particle decays, for example, the fermion comes and emits a photon. So energy is conserved, momentum is conserved. So well, the sum is the same. But of course, if the momentum p comes in, some fraction is preserved, and some fraction goes away to the photon. Now, so that's parameterized by this parameter z, which is in between 1 and 0. So that's a parameter. And there is some probability distribution for this parameter z. So you have to sample from some probability distribution of what this value z takes it. And this type of problem, which is a sampling from a probability distribution, is often done in Monte Carlo. So and because of that, people have written programs to do this type of problems in Monte Carlo, and people have written it, and people studying colliders use it all the time. And in fact, some of the papers are one of the most cited papers ever in high energy physics. Now, let's see. So and sampling is easy. So you basically want to find some variable which is uniform with respect to this probability distribution. And the important thing is that then you wish to find the inverse of this function, which is the inverse of integral. If you can easily find the inverse of the integral, and you can sample it nicely. So this is like a one-on-one of the Monte Carlo. I'm sure some people in the audience have used it much more than expert than me, but at least that's the classical thing, classical Parton shower. Hopefully this is clear. Now, let me come to the quantum, why quantum matters in any of these stories. So that's the question. And in fact, most of the time, people don't care about the quantum. So there are, as I said, like tens of thousands of papers have written, and they don't care so much about the quantum aspects. But in general, it's actually important, obviously, because the word is quantum in a sense. So, but if you want to discuss the quantum effects, quantum interference in this case, you might need a little bit more complicated situation. For example, suppose that instead of having a single type of fermion, suppose that there are multiple types of fermion states, like fermion of type 1 and type 2, for example. It's a qubit. It's described by a qubit. Now, and then, so this is I, but it's upspin or downspin, etc. And then when two photons are emitted, it changes a different state from state I to K to J. Well, okay, so I have chosen a specific K. But if you're interested in the final state, J, and the first initial state, I, they are intermediate states, which is simply summed up in this amplitude. But if you want to compute the probability, of course, you need to take absolute value squared, which means that there is a cross term. So, well, of course, sorry if this is completely trivial, but at least this is interference effect between different intermediate states, which is very, very important. And this needs to be incorporated. And in order to incorporate this and into the simulations, it will be essentially very difficult in the classical Monte Carlo simulations, simply because it's quantum. So it's not that easy to simulate, especially if the number of intermediate states grows exponentially. I said 1 qubit up, down, but it might be n qubit, for example, and then there are 2 to n states. So and then it becomes increasingly difficult to simulate this. So it's more natural to really simulate the state itself as a quantum state and do the quantum circuit, quantum algorithm to try to simulate that. So that's what we're going to do in connection with this quantum Parton shower. Now, let's see. Now, there's a little bit, you can try to make the situation a little bit more realistic. For example, I said previously, there is a momentum information, for example, momentum fraction, for example. And that makes the story a little bit more complicated also. Once you consider this type of algorithm in the multiple steps. well, for example, suppose that here in the step n, there is emission of particle, so the photon. And then you can talk about the energy of the momentum, etc. What is the momentum here, etc. But of course, the momentum there depends on whether the emission has happened or not in the step before, n-1 step. So if the emission happens, well, it means that some of the energy momentums are carried away. So you have less energy when it comes into here. And then you have to change the probability distribution here as well, because the momentum is different. So this probability depends on the momentum. What is the and that's yeah. So there's a formula, etc. But there are some subtle it might enter in the subtle way. For example, it's determined physically by some coupling constant on some gauge theory, and that depends on the energy scale through renormalization group flow, for example. So, but that's not important. And what is important in general, the emission probability itself depends, for example, on the momentum, and hence depends on what happened before. So it depends on all sorts of history. So if you want to discuss what happens in n step, you need to know what happened before, all the steps, n-1, n equal 2, etc. And you need to keep track of such data before, like what type of when it's sampled, what type of z you have chosen before, if the emission has happened, for example. And also the actual story is even more complicated because, for example, this is a little bit more realistic picture, and you might notice that even the number of particles are in general different in time. For example, here one photon is emitted, but at some point photon might pair create. Okay, maybe this arrow, the direction of the arrow should be opposite, but E plus E minus, or for example, Kuokyo bar. So some pair of particles are created, which in turn emits a photon, etc. So things are very complicated. And so in this, in general, what you should do is that you should remember there are multiple such particles. And whenever do some emissions, you need to remember which particle emitted what, for example. And then what is the value of the energy from momentum fraction in that emission, for example. So you need to keep track of all these parameters. And these are you'd imagine that it's best to keep track of these parameters in terms of classical data because it's a value of the momentum, etc. Now, of course, so you naturally come to the hybrid of classical data processing together with the quantum part, quantum circuit, which deal with the interference part. And the idea is that you can make a combined algorithm. Well, of course, things are not completely trivial because if you look at what people do with the classical algorithm, a lot of things are done, but you want to separate the quantum circuit. And in the quantum circuit, you do the whole process for all steps, you measure it once, and then that's it. You cannot say, oh, let's go back there, extract the information, go back, etc. So because once you measure it, everything is not everything, but at least the qubit you measure is gone. So you need to come up with some good way to separate the classical problem with the quantum problem, and that's the challenge. And we have come up with some version of that, but the actual problem is complicated, just like this one. So there are many particles, etc. So let me explain that in a much simpler problem, and for what this happens. So let's see. So the situation is the follows. So here I have, in general, it's a very abstract way of writing. And it makes the situation, but it makes the situation set up very, very general. So here I have some quantum state, which is denoted by Q, and the classical data, which is denoted by C. So this, for example, includes what happened before, what was the momentum, what is the value of the energy fraction, etc. Now, so all these data are there for at some step. So we're going to step one of the steps. They're going to repeat the amount of steps many times, but let's say at the beginning of the step n, for example, we are given this data. Now, I want to sample from this parameter z with some probability distribution, which is denoted by f. And I'm going to assume that f is much smaller because the step size is very, very small. And then, okay, so you can, well, of course, the z is a parameter. So if you integrate it, that's all the emission probability. So this is the emission probability with energy fraction z. So if you integrate it, you get a total emission probability. And if you subtract on 1, that's the, oh, okay, so it's hidden, but it's if you subtract on 1, okay, is there a way to hide it? Yeah, so let's see. So, okay, probably I just click it. Oh, sorry. Okay, there. Okay, that wasn't good. Let's see. Yeah, so okay, so then if you subtract from 1, that's the no emission probability, for example. Now, okay, so then the question is that you want to sample from some probability. Oh, okay, now it begins to start. Okay, so what is happening? So okay, so so here we are going to sample from some probability distribution, and here we have chosen a particular state, and you have to sum over all the quantum states, right? So and then this is the probability distribution. And we want to sample from here, and we just do it. But it's a little bit tricky because if you, as I explained before, in order to sample nicely with the important sampling and all that, you need to know the inverse of this integral. Now, well, of course, this f itself might be known, but it's a sum, many sums in general. If the number of states is large, it's a sum and then integral, and then you have to take an inverse. Well, maybe there's a clever way to do that, but in general, it's okay. So you can integrate itself, but you have to sum it over and then take an inverse. So it's not necessarily the easiest, at least. So you might need to come up with some little bit more clever trick to how to do the sampling from here. Hopefully clear. So it's just the quantum state. There's probability distribution itself is determined by the quantum state, and you want to do the sampling from there. So that's, I think, a very general problem. Now, there is a nice clever technique for analyzing that. And that is the Veto algorithm. In fact, technically, that's the most important contribution for this particular project. So let's say you are interested in this probability distribution. But instead of analyzing this directly, you're going to bound it by some another probability distribution, which is independent of the quantum state Q and satisfies inequality. Well, in practice, you want to choose F over to be as close as F possible. But of course, it's independent of Q. So sometimes it's a strict inequality. But let's choose some function. And then usually want to take F to be simple. For example, if there's a probability distribution something here, maybe you take it to be some very simple thing to bound it, for example, or make it even linear, something like that. So you can make bound the probability distribution by a very simple function. So that's F over. Now, once you have F over, you're going to try to sample from here. So this was the probability distribution before, but instead I'm going to replace it, the probability distribution, by over distribution. Oh, sorry, there should be no Q here. But there is a Q here, which is technically correct, but there is no Q here, actually. So there is no Q here, which means that you can sum it up. So this is normalization factor, which is 1. Alpha is a coefficient in the state. So so you can kill it, and this is a simple function F over itself. And then you can do the sampling. Well, of course, this is not the original answer. So you have to do something to correct it. And in the classical setup, people do the Veto procedure. So namely, this is the original probability distribution. This is the larger one. And choose some uniformly distributed parameter between 0 and 1. And if this combination is smaller than R, then you reject it, which means that nothing happens. So because you're overestimating it, and then you're going to reject it with penalty. And then you can show after some computation, then this gives the correct answer. So this is the extra procedure, Veto procedure, which gives the correct answer. Overestimate and Veto. Now, this is a classical procedure, but now you have to do it with the quantum procedure. So you have to apply the Veto procedure, the quantum case. And it's not trivial how to implement that in the quantum circuit. For example, we thought about adding 1 qubit for the Veto procedure, etc. But then that quantum qubit is entangled, etc. So sometimes it has unexpected consequences. And in the end, this is the as of now, things are moving. But as of now, this is the circuit we found, which is actually very simple. So so here, if you start with the state, and this qubit, this is 1 qubit. So this is a state. In general, in this case, there are only 2 states, but they can be multiple. Okay, so let's suppose here, in this case, there are only 2 states. And here, it's a qubit for keeping track of whether the emission has happened or not. Now, here, I'm going to sample from this probability distribution, F over. There is a hat to normalize it. And then, okay, and then you're going to sample from that over sampling, F over probability distribution. And then I'm going to do something afterwards. So depending on the state, you have a different probability distribution. different emission probabilities. So you have to change, you have to rotate this emission state. So 0 is no emission, 1 is emission. And you have to do the control rotation to let the emission happen. Now, when you do the rotations, you're going to rotate by angle. And this angle itself, you're going to determine from this F. So F total is the sum over all the possibilities. So in this case, there are two, F0 and F1, and F total is the sum. And then this causes the let's see. So here in this case, there is no well, the Veto procedure is kind of hidden in this angle, and so what we have shown is that you can just work out what happens to this circuit, and then show that it gives the correct density matrix under the assumption that this F, which is emission probability, is very small. Namely, the time step is reasonably small. So now this is a single step, but for example, you can try to make it to more states. For example, here in this case, there are multiple states, and well, in this case, you need one more sampling in a sense, because first of all, there are multiple qubits, for example, which is like a multiple particles. And in that case, you need to first do the sampling to decide which particle we are going to discuss. So we're going to decide there is a relative probability distribution between different particles. First, you sample, and you find that you're going to discuss, say, this particular qubit. And then you're going to do what was done before, for example, and then repeat the same procedure. So I can keep going, and there are more pictures in a paper. But first of all, what's important is that so we can show that we have cook up some simple quantum circuit, which gives the correct density matrix if this F emission probability is very, very small. And this we can show just by direct computation. And we can incorporate multiple states of the multiple states in the quantum state, multiple qubits. And also, what I explained so far is just one Monte Carlo step. Of course, you have to talk about 2 Monte Carlo steps, 3 Monte Carlo steps, and then quantum interference becomes more and more important. And moreover, you can try to upgrade this to the more complicated situation, the actual quantum Parton shower, involve many, many particles and many decay patterns. So that is the thing. And then I should first, before ending, I should first say that, well, if the state, okay, so here I assume that there is some state is given when we start the quantum Parton shower. So what is that? Well, you know, how complicated the computation is, as you might imagine, depends on how complicated the initial quantum state is. Now, if the simplest situation is like a product state, so suppose that the initial state quantum state is just a product state. And it turns out, in this case, it's actually, you can simulate it essentially as far as I know. So because previously there was a sum over all the quantum states. But in this case, you can, if you do the, if you follow our algorithm, it turns out that when you try to sample, it's just a sum of 2 probability distributions, which I believe you can do. So it turns out that if the initial state is simple, you can actually classical simulate it. So in the end, if you like, you can say that we obtained a classical algorithm in the end. But that depends on the initial quantum state. So okay, so let me try to summarize. So what I explained is the Veto algorithm for quantum Parton shower, and it turns out that this algorithm, partly because it's classical quantum hybrid. So as I mentioned at the very beginning, people have written papers about the quantum Parton shower these days. Several papers have written. But as far as efficiency, for example, number of gates, etc., is concerned, our methods are much more efficient. And in some cases, even there is even a simulation by classical devices. Now, so this is all I want to say. But then the question is, obvious question is that, okay, so could there be other situations where this type of problem applies? And the main message is that it arises, as far as I know, it seems to arise whenever there is a situation of sampling from some probability distribution determined by quantum state. And so said that way, that could be interesting. And perhaps some of the details of what I said here as to how to incorporate the state, etc., could be useful in other contexts too. Thank you.
Thank you for the nice talk, Masahito. Any comment or question? Thank you for the nice talk. I have a question. Can you comment on like how those initial states look in realistic situations? Because you mentioned in the beginning fermionic state, but there was a single fermion as far as I understand. So are those states correlated? Because on the quantum info site, there are some cases like when you sample fermions, it can be easy.
So that's a very interesting question. And in general, so that will depend on the specific models. For example, here we are talking about some dark fermions, etc. So it might come from the decays of Higgs or decay of some other vector bosons, etc. It might depend on the scenario. But perhaps one scenario what I can think of is that, for example, suppose that whatever physics preceding that is independent of such flavors, for example. So it's like a gauge coupling. For example, gauge coupling, gauge series tends to be universal for all the flavors. Gauge interaction is universal. And in those cases, typically you get kind of an entangled state, I think, between different flavors. I don't know if it is true or not, but that's what I would imagine, actually. Yes. And then sometimes, so, and in fact, partly because of that, well, it's not in the different flavors case. For example, it might be easier in the situation where particles decay, and then there is particles emitted in two different directions, for example. And in that case, people expect that there is an entanglement in between, for example. And people even try to use such entanglement to try to for example, test the Veto inequality, for example, in a particle physics experiment, for example. So of course, it's not the easiest experiment, but people are taking very refined data anyway. So I think it's an exciting possibility of trying to have to incorporate, whether we can use the particle colliders to test the quantum, basic quantum theory. But also people also try to incorporate some of the quantum information type things to the data analyzing. For example, like a post measurement, like a weak measurement type things, for example. And then there are some discussions of post processing and weak measurement, and that may enhance, that might reduce the error bar by factor 2 or 3, etc. So it's of course you're throwing away a lot of things, so it's a little bit delicate question whether you can actually gain it or not. But at least you can try to do the analysis, and people have already taken the data. So by just changing the analysis, you might be able to reduce the error bar, for example. So I think there are a lot of interesting questions along those lines, and this might be some example of that. Yes.